Hey everyone, this is Dr. Walker. This is video 59C, and we're going to look at work and energy when dealing with rotational motion. When an object is rotating, it's going to have an energy due to its motion. This energy is called a rotational kinetic energy. It's defined as K sub r equals 1/2 I omega squared. We can quickly see where this comes from. It comes from breaking up a rotating object into a bunch of little mass elements mi. These little mass elements have a linear speed vi. We can look at the kinetic energy of one of these little mass elements. It's going to be 1/2 mv squared. This is the regular linear kinetic energy. We can substitute r omega for v initial, for vi, to get this expression. That's the kinetic energy of one little mass element, so to get the kinetic energy of the entire object, we just sum up over all of these elements. When we do this summation, we'll see that we end up with the summation of mi ri squared, which is the moment of inertia. So this is where this energy comes from. Each individual little mass element has a linear kinetic energy, but the object as a whole has a rotational kinetic energy, which is measured in joules. Now let's look at work on rotating objects. We know that work and energy are very closely related. Let's consider a force acting on this object and causing it to rotate. It's going to rotate with an angular speed omega. Let's consider the work done by this force as this point here on this object just moves a very small distance, ds. d theta here is the angle that subtends this distance. Typically it's an arc length, but because it's so small, we can just say that it's a straight line. Let's find the work done for this infinitesimal rotation. Work is defined as the dot product of the force and the distance. We know that a dot product usually uses cosine if we have the angle between ds and f. But in this case, we're defining another angle phi, which instead of being between ds and f, instead of being this angle, is going to be between the r line here and the f. So when we're doing this dot product here, instead of using cosine, we're going to get sine of f sine phi ds. This right here is the ds, so we've made another substitution where ds equals r d theta. We've seen this substitution before. If we think of ds as an arc length, then it's defined as r d theta. We can make one more simplification. Can you see what it is? We have f sine phi r. What does that look like? Well, that looks like torque. So the work done for an infinitesimal rotation, this dw is equal to torque d theta. It may look a little bit foreign, but it's similar to what we saw before for linear motion. Before, when we talked about a work, it was a force and a distance. Well, now it's a torque and an angle. The next thing I want to look at is how is work related to energy? What we want to do is we want to go ahead and rewrite dw equals torque d theta, but we're going to write it in terms of omega instead of theta. Let's take a look at the side as how to do this. The first thing we're going to do is we're going to rewrite torque. We know from Newton's second law that the net torque is I alpha, which can be written as the derivative of omega with respect to time, the alpha. Then we can use a chain rule here. And then d theta, derivative of theta with respect to time, is omega. So we have rewritten torque as I d omega over d theta times omega. Now we can multiply the d theta to the other side. It's going to give us torque d theta is I omega d omega. Torque d theta is what we wanted to substitute. So now that means that we can write our d work, or infinitesimal work, as I omega d omega. Now we can integrate this work to get the total work. Let's see what happens. When we integrate this work from our initial to our final angular speed, we get 1/2 I omega f squared minus 1/2 I omega initial squared. So this tells us that the work done on a rotating object changes its rotational kinetic energy. Does this look familiar? Hopefully it looks like the work kinetic energy theorem. And that's exactly what it is, but it's for rotating objects instead of objects moving in a straight line. We can expand on this just a little bit and say that the work kinetic energy theorem not only changes the translational kinetic energy, the 1/2 mv squared, but it also changes the rotational kinetic energy, 1/2 I omega squared. When we have an isolated system, we can write conservation of energy as the change in both types of kinetic energies plus the change in potential energy, and that's going to equal 0 for an isolated system. We can definitely rewrite this expression if we want, with the initial energies on one side and the final energies on the other. I suggest doing it just for practice. So 1/2 mv initial squared plus 1/2 I omega initial squared plus, let's say we're only dealing with gravitational potential energy, mgy initial, all the initial energies equal all the final energies. That's another way to write conservation of energy for an isolated system. I have a picture here of an Atwood machine. You may be wondering, why is this here? I thought we were done with this. We did this when we were talking about Newton's second law. But when we were talking about Newton's second law, we always said that the pulley was massless and we ignored the effect of the pulley. We only looked at the masses that were moving up and down. Well, now we don't have to ignore the fact that the pulley has mass, it has a shape, and it definitely affects the motion of these masses. So we'll be doing an example soon where we can figure out the speed of the masses or how far they move without neglecting the effect of the pulley, which is going to have the rotational energy component, while the masses that are moving up and down will have the linear kinetic energy component. Before we end this video, I wanted to talk about one more topic, which is power. We know that power is the rate at which work is being done, or the derivative of work with respect to time. We can substitute torque d theta for dw, as we just saw in a previous slide. And then we can say that d theta, the derivative of theta with respect to time is omega. So now we have an expression for power delivered to a rotating object. It's torque times angular speed. This should look familiar because for linear objects, for power, we had a force times a velocity. Let's go ahead and take a look at some examples.